Well, welcome to the final regular session of Pycon 2013. For our grand finale, short of the closing remarks, we have log analysis with Pandas with Tavi Burns. Please give him a warm welcome.
Thanks. So, who here has used IPython Notebook? Oh wow, okay, so I'm preaching to the converted today. Who's used Pandas? Almost as many, okay, cool. So I'm going to talk about how you can do log analysis with Pandas. I'm also on the board of directors for Pycon Canada. We had an awesome conference last year in November in Toronto. We are doing it again. We have a venue in Toronto, August 9th through 13th. So come check out the website, pycon.ca, soon, when we have this year's up and going, probably in a couple of weeks, or on our Twitter account at PyconCA. So let's get down to business. Log analysis with Pandas. As I guess most of you know, Pandas is an open source BSD licensed library providing high performance, easy to use data structures and data analysis tools for the Python programming language. Wes McKinney also wrote this wonderful book to go along with his wonderful library. I used the early release version of the PDF in making the presentation, so thank you very much to Wes for that. Is Wes here somewhere? Maybe? Woohoo! Thank you. Wes also fixed a bug in Pandas last night that you will not see in the presentation. So thank you very much for that. Pycon is wonderful for things like that. All right, let's dive right in. If you're on a Mac, then you'll need to install things like ZeroMQ and FreeType to get matplotlib and the notebook happy. If you want HDF5 support, and you do, you'll also need to install HDF5. On an Ubuntu box, the libraries are approximately like that, and for HDF5 support. And for the Python packages, you need IPython, PyZMQ, Tornado. That's because the notebook is a web-based format. NumPy, Matplotlib, and Pandas. I occasionally find that I have to pip install things one at a time because the first thing doesn't get fully installed and then the second depends on the first. And then for HDF5 support, you need Cython, NumExpert, and tables. Then you run it from the console. IPython Notebook Pylab inline. And it pops up in a browser. And you can do things like write Markdown and Python. And evaluate it. And the output shows up in the notebook. It's nice and handy. When we're using Pylab, we get an interface that looks very much like MATLAB, except it's Python. So we can do things like do a line plot. We can define a data set, just the numbers from -100 to 100. We're going to do a cubic plot, so we can plot the data, which is the x values, against the y values, which is the cubes of all of those. We can give it a nice little label. You notice a bit of LaTeX syntax here with the dollar signs on either side, and Matplotlib will very happily format a nice little math equation for us. So that's kind of neat. We just get a plot inline in our web page. You can do histograms as well, which can be really useful for doing log analysis when you want to see what's the distribution of response times. In this case, we can just get a Gaussian distribution and say, show me a histogram. And we get a nice little bell curve. So, Pandas Crash Course, when I did the very first version of this presentation, it didn't have Pandas at all. It was actually just pure Python, how you can do MapReduce-like things. But Pandas is really what you want to do. It's a lot faster, a lot more powerful in the end. And so I found that some people needed a little bit of a boost if they haven't been exposed to NumPy. NumPy has some very interesting ideas that are really useful to us, and we need to understand those just a bit in order to take advantage of Pandas. So Pandas has a data structure called a series, which is a one-dimensional, homogeneously typed list. We can give it a Python list of integers, and we get as output at indexes 0, 1, and 2, values 1, 2, and 3. And the D type, which is a NumPy thing, the data type for that is int64. We can also introspect directly, what is the D type of this thing? Yes, in fact, it is int64. If we pass in something that has some floating point, then we get back a series with float64, and we can mix things up. In Python, everything's an object in the end, so you can get a series with D type of object. One of the really cool things in NumPy and Pandas is broadcasting. So if you have a series, you can take a unary or binary operation and apply it across all of the elements. So we can say A is the series of 1, 2, 3. We can say A greater than 1, which will apply element greater than 1 to all of those elements and return us a series of Boolean values. 1 is not greater than 1, false. 2 is greater than 1, true. 3 is greater than 1, true. You can do it with double equals as well, and you can map your own callables using series.map. You can say, tell me which ones are even. So composing series, you get data frames. Data frame is series as columns and rows having a shared index. It's a little bit like having a SQL table in memory. So we can construct a data frame here out of a list of lists, where the first column have integers, the second column is floats, the third column is mixed, so we get objects. And we can pass in a separate list as the indexes that we want along the left-hand side. And the IPython notebook makes this really handy by giving us a beautiful little HTML table with bolded headers and everything. And if we ask for the D types of this data frame, it'll tell us the integers column is int64, the floats column is float64, the objects column is object. And I guess overall, it's objects. For selecting data out of a data frame, you can use subscript notation to pick out the different columns. If you just want the floats out of a data frame, select single column from a table, you can just do that and you get a series of D-type float64. You can get multiples, like select foo comma bar from table, by just indexing by a list of the column names. You can use the usual slice notation from Python to get different rows, noting that these are Python slice indexes. They are not the data frame index values. So we're just selecting not the first 2 rows, the same way that we would normally do it in Python. If you need to access the rows by their index, then you can use the XS method on a data frame. Say you want the row with label 3, that's axis 0, label 3, and here we get a series that's the cross-section. It's a row of the data frame. We can also specify column names this way if you want to have a consistent way of accessing things, whether it's columns or rows. That's a nice way to do it. Now, there's one more way of fancily indexing into a data frame, and that's using a list of Boolean values. And this is a mask. So if the mask is true, false, the first row will be returned, the second won't, the third will, the fourth won't. It's a lot like Python's filter built-in, where you have a predicate that says, yes, include the data value, or no, don't include the data value. But the predicate responses have already been pre-computed, and we just apply them. So here we get the first row and the third row. And so with the conditional expression broadcasting, we get some really neat things. We can take the integers column from our data frame, ask for a list of Boolean values where the integer is greater than 4, and use that as a way to index into the data frame. So now we have all of the rows where integers is greater than 4. That really does sound a lot like SQL, doesn't it? It's nice and powerful, but all in pure Python. NumPy has the np.invert function, which will take a series or data frame, some NumPy thing, and give you the Boolean inverse. And this is a nice way to say, you know, I've done all the things greater than 4, now I want all the things I didn't deal with the first time. And these run incredibly efficiently over relatively large data sets. I'm not talking big data, I'm talking most of the big-ish data that you will ever deal with. Most people don't deal with big data. Most people deal with not huge data. So you can also get a subset of the rows based on an index value by using the special index attribute on a data frame. So you can say, where the index value itself is greater than 2, give me just those rows. I like thinking in pictures, so I drew up this little picture where you've got the data frame on the left, and we have the mask in the middle, and you can sort of think about it trying to squish the data frame through the mask, and only the values that are on the true bits of the mask end up in the output. So we have some logs. Unfortunately, how to get them into a readable format is really beyond the scope of this presentation. People store logs in so many different ways. I have yet to, but I've heard it's a really good idea to log things in JSON. It makes it really easy to parse, but you'll still need to interpret things out the other end. One thing that I've had to do, even to get the CSV format you see here, is to read multiple log lines from the beginning of a request, from the middle of a request, from the end of a web request, and put that all together to represent one row of the CSV file that says, yes, this is all the important information that I have from this entire request. And writing those, sorry, up to you. You can come talk to me later if you're interested in how I can do that relatively efficiently. But I'm going to assume we have it in CSV already, or something else like that. From a CSV file, it's really easy to get that data into a Pandas data frame. There is a wonderful read CSV function. And you give it your opened log file, and you can say, yep, here's the column that I want you to use as the index. In this case, I've got a POSIX timestamp as the first column, so I say, yes, I want you to parse the date on this column. Except that POSIX timestamps aren't really a common format, so I have to pass in my own callable that says, this is how you turn a string representing a POSIX timestamp into a Python datetime. Importing 1.8 million records takes about 55 seconds on my laptop, unless I disable garbage collection. Python garbage collector is only interesting when you have circular garbage, bits of garbage that refer to each other but are not able to be referenced from anywhere else in the Python interpreter. In the process of loading up 1.8 million records, we're never creating circular garbage. We're loading up a lot of these strings and slicing them up into smaller strings. They're getting loaded into tuples, and then they're getting put into NumPy arrays and Pandas data frames. And at the end, it all gets cleaned up. Disabling GC cuts time a lot. It's unfortunate that you have to do that to get the performance you want. Loading up a second data set takes about 20 seconds longer. The third data set takes 20 seconds longer than that. It grows with the size of the Python VM. So we'll disable the GC, we'll load up our data set once, and then we're good to go, right? Well, yeah, we have a nice little data frame. We have all the nice columns. We even have that POSIX timestamp turned into a very nicely formatted datetime that we can read. In UTC, notice. It's not in local time. So really, you don't want to have to reload things from CSV all the time, so you want to use HDF5. And Pandas has a beautiful interface to HDF5 that's a lot like local storage in a web browser, where you get this dictionary-like thing and you can just put your data frames on it, and it'll make sure they go to disk. And then you can load them up from disk later. So we see we have a store, it's stored on some path, we've got a data frame, it's got a shape, it's only one row, but it's 12 columns wide. I can delete the store from the Python interpreter, reinitialize it by just saying, yep, this is the store that I had, and what was the data in there? Yep, that looks like the same data. And that works really, really well. Instead of taking 35 seconds to load up 1.8 million records, we can see here I've got the data from May 7th sitting in a store. This is a subset of the data from May 7th last year from one server. And there, I just loaded it, 1.8 million rows. It's at the speed of I/O, just basically straight into memory. That makes it really easy to iterate on things. If the Python interpreter crashes or if it takes too much memory, you can kill off that IPython kernel, restart it, rerun the cells, and you're good to keep going. So in this case, let's try to make that histogram and show what's the distribution of response times from our application. So in this case, I'm going to define a set of base 2 log bins from 2 to the negative 10 to 2 to the positive 10. And we can just say, hey, give us a histogram of the elapsed times, and here are the bins that I want. And it'll say, here are the bins, and here are the values. Wow, we have a nice little graph. And we can see that a huge number of our requests get served in under 100 milliseconds. That's not too bad. Maybe one day you notice there's a big slowdown, and we did once, where the bars all got shifted one to the right. Everything started taking twice as long. We're like, that doesn't look right. And we looked through things, and it turns out we were making one extra spurious SQL query that we didn't have to make on every single request. So it can be really handy as a debugging technique to look through and see, you know, where did these things shift? Why are they shifting? But the big thing when I started and really got sold on the IPython notebook was when I had to when we were looking at improving performance for larger responses to clients. And so I want to see, is there a correlation between the response time and the response size? One of the data points that we record is how many database rows, give or take, were returned for a RESTful style request. So if you asked for a list of invoices, we might have returned 5, we might have returned 1,000. And is there a correlation in times? And that's, as you can see, incredibly easy to express. I can just say, plot the elapsed versus rows as a scatter plot with dots. And we can see, yeah, there are a couple of different trend lines, but overall, longer requests take longer because they're bigger. And it is a little generic. It's looking at all requests, and we can do better. And in particular, I was looking at I'll get to that. So we do deployments at about 9 a.m. on Tuesdays. That's our standard release time, 9 a.m. Toronto time. So let's figure out what May 7th, the Monday, and May 8th, the Tuesday, look like at 9 a.m. So we'll localize the state times for Toronto. So Toronto's local 9 a.m. as UTC, and make it a naive date time so we can compare them. And I made some interesting changes on the 8th to improve specifically the invoice requests. We had a bunch of DTO-like things, much like Mike Prinat was describing a couple of years ago in his presentation. And that was the inspiration for me to go and meta-class a bunch of our DTOs. It improved performance a lot, it improved memory use, a lot of very interesting effects that we weren't expecting. But it's really good to be able to quantify that. So let's look at the May 7th data after 9 a.m. by looking at May 7th, the index, which is the date time, that's greater than or equal to 9 a.m. And specifically, we're going to look where the general kind of request we're looking at was for the invoice resource. And we can see that down from 1.8 million records, only about 284,000. Starting at 1 p.m. UTC, which is 9 a.m. in Toronto, all the way up to about 4 a.m. the next day UTC. And we'll do the same for the 8th, the day of release, and we get about 263,000 entries. And then we can plot them. Using the MATLAB-like interface, we can say, here's the title for the plot, here's the X label, here are the limits. There are uninteresting outliers past 30. Plot May 7th in red dots, plot May 8th in blue dots. And we can see that, yeah, they still have the same trend line, but on the 8th, it took less time to serve the same number of records in a request. Okay, that's really neat. Was it my changes to invoices that actually caused this improvement? Let's check estimates. Estimates have a very similar form to invoices. They look the same, they have the same kinds of internal data structures, but I didn't change very much in estimates, only the bare minimum shared code between the two. And so we can see that, especially at the bottom end, estimates didn't change their behavior. At the top end, there's a bit of difference, but invoices get maybe 10 times the amount of traffic that estimates do. If we just made invoices significantly more efficient, especially for expensive requests, that probably had a systemic effect on everything, making everything just a bit faster. Well, from the promising plot we saw first, I was like, okay, I should really actually do the rest of the work, see if estimates are going to be that much better. So we do the same change, we go through the same code, largely copy-paste. If you need to do these kind of analyses regularly, you should factor that out. And yes, in fact, the week later when we changed estimates, we see exactly that same shift, especially in the low end, where it improved performance. So this is really good as a developer to see. It's like, I made this change, and look, it means that people have to wait 5 seconds instead of 10 seconds for a request. That's a really big difference, especially in the web when people get impatient. They wait 4, 5, 6 seconds, they're like, I don't see anything, click again. Well, now your server has twice the normal load. And this still hasn't responded to the second request. Oh, click again. Oh, now you've got 3 processes running on the server. You can very easily fall over. So, yes, that's good. And you can take this to your manager, you can take this to management, and show them, thank you for letting me work on this. Not only did it lower server costs, this obviously has to make users happy. They're going to be way happier not waiting an extra 5 seconds. So one last thing that that I don't think was particularly well supported in Pandas a year ago, but that works beautifully now, is taking these kind of events that come in at irregular intervals, and I know when events happened, and I want to aggregate them, as opposed to things like stock ticker data, or I have a temperature measurement once per minute, and I want to see trends. We have these log records. I had 15 requests in the first second, 18 in the second, but I just want to know minute by minute what's the median response time. And so we can do that very easily now in Pandas. We'll take the May 7th data, we'll look for just the first 10 minutes, just so that we can actually see the concrete data values here, and we'll take the series of the elapsed request time, resample it by capital T, which is a shorthand meaning per minute, using NumPy's median function, and it looks like our median response time is about 32, 33 milliseconds, around midnight. And data frames also have this very handy plot method. So you can say, take the May 7th data, the elapsed characteristic of that, resample it by minute. How are we going to aggregate that? By taking the median and just plot it. And we get a nice graph, just like you'd get out of Graphite or Munin. This is a little more code than having Graphite already up and running. But as we just saw, we have an incredible power over what is the data set that we feed to this plot function. If you want to know what's the median response time for just invoices, you can do that. What's the median response time for this particular account? You can do that. You can compare this account over the course of weeks. You can see, hey, are they doing something funny? All kinds of interesting things. And it's really easy then to define how we want the downsampling to occur. We can use NumPy's percentile function to get a nice little stacked graph of the different percentile response times. And sometimes when you make a performance improvement, you might see the bottom end drop off. You made everything a little bit faster, but the really expensive requests are so expensive that it doesn't make much difference at the top end. Other times there were changes that I've made where the 50th percentile didn't change at all, 75th kind of changed a little, but 95th percentile dropped 40%. And that, again, is probably the bigger win for your users in terms of interactivity and how your app feels. So, that is the presentation. I have the slides up on my website already. You can download the IPython notebooks. The NB viewer is a wonderful way to actually view the notebooks online without having to install anything. There are PDFs for those who need those. And as I said, thanks to Wes for fixing bugs. You'll need Pandas 0.11 dev from GitHub as of last night in order to actually run these things. They do all run. The one exception is that example data that I had from May 7th and 8th. Actual production data, so I can't share that. But I have the example one line. You can generate your own data, fictitious or otherwise, and play with it. So. Are there any questions? There's a microphone over there. This is going to be good.
I just had two small comments. So first of all, I'll show you how to fix the code so that you don't need the development version. There's a workaround that's a bit simpler than what we were chatting over email.
Oh, okay.
And secondly, I'm pretty sure that the log file import time most of the time is being spent in the date conversion. So there's some ways that can improve that also.
That is also entirely possible.
So if you're calling that Python function 1.8 million times, that's going to end up being probably one of the big bottlenecks I would expect.
Yeah. So the trick I don't know is that when I turn off GC, the time drops significantly. So
right.
Of the 35 seconds, a lot of that that's probably the date time.
And that's because there's a lot of, I think, GC time, and like the temporary integers that you're creating are being GC'd.
Yeah, the temporary integers, the string slices along the way, I think somewhere in the CSV reader, because I wrote a similar one in pure Python that was using the Python CSV reader, and I think it's building up tuples internally, and those things will get garbage collected in this case, but by ref counting, not by circular garbage. So. Oh, thanks.
So I just had a quick question. I was wondering if you were actually using Pandas for this log analysis on your web servers as a, like, not necessarily real time, but on like a regular basis, or are you just kind of doing this on the side on like your deployments, or like kind of from the IPython notebook?
So typically using IPython notebooks for this kind of thing, I use it for exploratory purposes. So there's a particular release, I know I'm going to release this particular bit of code. I want to be able to judge, did it change things or not? I think at the time I also had Graphite running in a real-time mode, tailing the logs, so that I could see the real-time change. Oh yes, good, that fixed things, or at least made things generally faster. Like I said, the 95th percentiles would drop a lot, but I wanted to see, was it exactly my change that changed this very narrow subset of the app? And to do that in Graphite, I'd have to go and change a whole bunch of code that I generally don't need to change. So I'd use the notebook for the exploratory work, and if you find something that you want to have again and again and again, that's something that you want to put into a plugin or something that throws data into Graphite, or even writing a Munin plugin. So for just the percentile response times, I actually gave a script to ops and said, can you just run this for Munin? Munin has its own formats, it runs every 5 minutes, and we get Munin graphs for ops purposes.
Thank you.
I have a question. Okay. What would you recommend for a pathway if I actually want to take SQL data and take that straight into Pandas?
I think there is, like the read CSV function, I think I remember seeing one that can suck in SQL. Yeah, so there's something similar to read CSV, but it's like read SQL. So if you've got, I'm assuming a DB API driver, maybe SQL Alchemy? Okay, there are things in Pandas that know how to suck that kind of SQL data in. And Wes has done talks on just Pandas and the kinds of joins and things you can do. It's really powerful. I've only barely scratched the surface here.
So the IPython notebooks are terrific for passing around to developers and really impressing them with plots and everything. But if you're dealing with like business and management folks, those notebooks they might like the graphs, but the notebooks could freak them out. Do you have any recommendations on ways of making an IPython notebook and then converting it to something even more friendly?
So using the NB viewer is nice. So if we go to the introduction slide I linked directly, the notebooks are in a JSON format, so we get that. But NB viewer is hosted from ipython.org, and it will render the notebooks for you. So you can just post your JSON notebook online, and you can give management this URL, and all they will see is this beautiful thing that's not interactive at all. It's just static text, but with all the highlighting, all of the images already in line. For PDF, I literally just went Command P in Firefox, and I got PDFs. They're a little bit ugly. I know that Fernando was talking at Pycon Canada about ways of exporting notebooks into PDF, into this format, into LaTeX, so that you can create even professional academic papers from notebooks directly, so that you know that the code actually executed, the tests actually ran. This is a reproducible result.
Well, thank you very much.
And data analysis tools for the Python programming language. Wes McKinney also wrote this wonderful book to go along with his wonderful library. I used the early release version of the PDF in making the presentation, so thank you very much to Wes for that. Is Wes here somewhere? Maybe? Woohoo! Thank you. Wes also fixed a bug in Pandas last night that you will not see in the presentation. So thank you very much for that. Pycon is wonderful for things like that. All right, let's dive right in. If you're on a Mac, then you'll need to install things like Zero. Then you run it from the console, IPython Notebook Pylab inline, and it pops up in a browser. And you can do things like write Markdown and Python and evaluate it. And the output shows up in the notebook. It's nice and handy. When we're using Pylab, we get an interface that looks very much like MATLAB, except it's Python. So we can do things like do a line plot. We can define a data set, just the numbers from -100 to 100. We're going to do a cubic plot, so we can plot the data, which is the x values. So I'm going to talk about how you can do log analysis with Pandas. I'm also on the board of directors for Pycon Canada. We had an awesome conference last year in November in Toronto. We are doing it again. We have a venue in Toronto, August 9th through 13th. So come check out the website, pycon.ca, soon, when we have this year's up and going, probably in a couple of weeks, or on our Twitter account at PyconCA. So let's get down to business. Log analysis with Pandas. As I guess most of you know, Pandas is an open source BSD licensed library providing high performance, easy to use data structures, ZeroMQ and free type to get matplotlib and the notebook happy. If you want HDF5 support, and you do, you'll also need to install HDF5 on an Ubuntu box. The libraries are approximately like that, and for HDF5 support. And for the Python packages, you need IPython, PyZMQ, Tornado. That's because the notebook is a web-based format. NumPy, Matplotlib, and Pandas. I occasionally find that I have to pip install things one at a time because the first thing doesn't get fully installed and then the second depends on the first. And then for HDF5 support, you need Cython, NumExpert, and tables.
Well, welcome to the final regular session of PyCon 2013. For our grand finale, short of the closing remarks, we have log analysis with Pandas with Tavi Burns. Please give him a warm welcome.
Thanks. So, who here has used IPython Notebook? Oh wow, okay, so I'm preaching to the converted today. Who's used Pandas? Almost as many, okay, cool.